Welcome everyone to lesson 2.6 from Precalculus, which is all about competing function model validation. What that essentially means is that we've learned a lot of different ways to do regression. We've learned a lot of different models for regression. How do we know which model is most appropriate to use? So, without further ado, let's get started. So the big idea here is that, again, we have multiple regression models. Which one do we use when? Well, first and foremost, we could look at the context. If we are talking about something that is growing at a constant rate, we're going to use a linear regression. If we're talking about something that's change is happening at a constant rate, then we're going to use quadratic. And if its change is proportional, we use exponential. That's all fine and dandy, sure. But there are some nuances there, and there's some weird scenarios where you really just have to know, and if you don't know, the context doesn't help you. So, for example, if we're talking about a radioactive isotope, it's going to behave in an exponential way because it's got a half-life, and that's how radiation works. It works through exponential decay. Or if I take something out of the oven and I'm measuring its temperature, or I take something out of the fridge and I'm measuring its temperature that it changes, that is Newton's law of cooling, and that is exponential as well. But unless you knew that, that doesn't really help you. So context, iffy. Sometimes it works, sometimes it doesn't. In this course, you're not really going to have to focus too much on that, but it's a good validator if for the other two. It's like, yeah, I definitely know what I'm talking about here. The one that we've used a couple of times before is these R and R squared statistics that we have the calculator produce for us. And those are great. They work really, really well, but they're not the only way. Plus, we don't go into the nuance of the R and R squared statistics. If you take AP statistics, you'll definitely go into those and you'll understand those a lot better. But for us, like, besides seeing like 0.99, what's a good R and R squared statistic? Like, what's the cutoff between good and bad? We don't really know. And we're not going to get into it, but a statistics class would. So we are going to look at residuals as well. So first and foremost, we're probably going to use R and R squared most often, but residuals are our second way of really telling. So a residual is how much our model is off from our initial data. Error is very, very similar, and we'll talk about error in a second. But if I have this data set here, and you can't see it, but there is a faint line. Let's see if I can insert a line or not. It doesn't look like I'm given the option. So we can see we have a line of best fit right around here. It's a little hard to see because I stole the graphic from the internet. I'm sorry. So this is our linear regression. This is a plot of our residuals. So the 0 corresponds to our linear regression line. So if I look, for example, at this orange dot, the distance that orange dot is from the line is the y value of its residual plot. This point is a little bit higher, so it's a little bit higher in our plot. This point is even more off, so it is even higher. And it can be below. We have a point here that is below and a point here that is below, and those are there respectively. So that's how residual plots work. It is how far off you are from what we predicted. So to calculate a residual, you would take the actual value we have and subtract the predicted value from our regression equation. Error is the opposite, and I do mean opposite in the entirety of they have the exact same number, opposite sign. Because error is predicted minus actual, since you are flipping those two things, it's going to produce an opposite value. So if this is positive 2 for a residual, it's going to be negative 2 for error. Error, so again, error and residuals, kind of the same thing, but error's sign correlates to over and under estimates. So if an error is positive, it's an overestimate. If an error is negative, it's an underestimate, which means residuals have the exact opposite. Positive would be underestimate, and negative would be overestimate. We can see that here. These are negative residuals, and the curve is above them, so it's an overestimate. And these are above our estimation, positive residuals. They are an underestimate over here. So let's use this and talk about some more regressions. So we have a high school student is practicing with a pitching machine to improve their performance at bat. Each day they record how many balls were pitched versus how many they were able to hit. So the input here is the number of pitches that the machine produces, and the output would be the number of hits. Let's make a regression out of this. So we're going to turn our calculator on, go to statistics, enter. Again, if we have anything in our calculator, we're going to clear the lists. You can write over them, but if you have a different amount of data, this is really the major way to do it. So from this, I have no idea if this person's good or bad, but we can make a linear regression curve from this. So what we're going to do is, again, we're going to make sure our statistics give us all of the data. I just like having all the stat diagnostics on, me personally. Then we're going to go to stat, calculate. Oh my, I picked the wrong one. We're going to back to stat. We're going to go to linear regression, number 4. And like before, we're going to store our equation just so we have it to call back on later if we need to. Calculate. So we get a regression of, so this was m of t. M of t is equal to 0.417x minus 8.701. Essentially. Use our function to model the error at 50. Well, error is our predicted minus our actual. So let's plug in 50 and see what happens. So I'm going to go to table. Remember that if your table is not already set up to receive inputs, you go to table set and make it set to ask. We're going to set 50, and I get this number here, so I get 12.1395. Let's make that nice and easy, 12.14. At 50, we actually had 20, so we're going to take away 20, and this is a negative number, so we can already tell it's going to be an underestimate, which makes sense. 12.14 minus 20 is negative 7.86. So is it an over or underestimate? It is an underestimate. And we could say that because the error at t equals 50 is negative. So you can do all that. But it also just makes sense, right? Our function predicted is going to be 12.14. The person actually got 20. They got less, so the function predicted less than what they had. It was obviously an underestimate. So even though we're using all these big words, and sometimes we might have all these formulas, like, make it make sense in your mind, right? So not too bad. Honestly, not too bad. What about interpreting from a residual plot? I can tell you that this is something that I had to relook up because it's not something that comes up often, and I wanted to know, and I wanted to be able to teach you properly. So in this case, we had several cars that were tested for braking distance, and a regression model was used to calculate the car's weight versus the braking distance. So the input was the weight of the car, the output was the distance it took to fully stop the vehicle. So we have the residual plot here, and we have a point here that is 2,800 comma negative 5. What does that mean in context? So what that means for us is the residual is negative, right? So if the residual is negative, we had an overestimation. It's under the estimate, right? So the function, or the regression, the model. Actually, I like that better. Let's do the model. The model overestimates the braking distance at a weight of 2,800 by 5, what is the unit for the output? 5 feet. So the model overpredicts by 5 feet, essentially, is what that point means. So don't overthink it. It is as simple as it seems. And if it doesn't seem simple, that's okay. We can just practice with it. We can ask some questions. If you have questions about it, again, please make sure you ask me. Let's move on, though. So why look at residual plots? So we talked about before that there are 3 major ways to tell if a model is good or not. We can think about the context. We can look at the R and R squared values, which are great. But we can also look at residuals. So let's look at these models here. This data looks linear, and its regression doesn't have, and its residuals have no real pattern to them. This function, like this data, if I were to draw, this data kind of looks like an upside down exponential, if I were to guess. And we can see that there's a pattern to, there's like this parabolic pattern to the regression, to the residual plots. So this is what we would call a bad fit. Something else would probably fit better. And in this case, it would probably be an exponential. Here, yeah, the data points are all over the place, but the residuals are also all over the place with no clear pattern. So this would be what's called a good fit. It could be a good fit. But how good, like, good is relative. It's good relative to anything else. Is it going to accurately predict stuff for you? Probably not. But it's the better model. So you can think of it in that kind of way. Residuals kind of like, which one's better? Because nothing's going to predict data very well for that because the data's all over the place. That is it, though, for this lesson. If you have any questions, please make sure you ask. Otherwise, I'll see you in the next lesson.